Hello and welcome. Having gone through the fundamentals of set theory and some operation on sets, we are now ready to dive deeper. In this lecture, we will first learn to pair elements of two or more sets. We will call this Cartesian product of sets. After that, we will start imposing conditions on the pair of elements and develop the notion of relations. We will further restrict the pairing of elements and learn to define functions. After that, some examples of standard functions will be seen. Lastly, we will learn to perform operation on real functions. Now consider a set A having elements e11, e12, e13, etc. and consider another set having elements e21, e22, e23, etc. We can pair each and every element of A to each and every element of B. For example, we can pair E11 to E21 to E22 and to E23. And we can write these pairs as follows. We can write it as E11, E21, E11, E22 and E11, E23, etc. Similarly, we can pair E12 to E21 to E22 to E23 and write these pairs as E12, E21, E12, E22, E12, E23. The third element is paired to E21, to E22 and to E23, etc. and we write it as follows: E13, E21, E13, E22, E13, E23. The set of all the ordered pairs in this is called the Cartesian product of A and B, and it is denoted as A cross B. Now we can formally define Cartesian product of sets. For two non-empty sets A and B, their Cartesian product A cross B is the set of all ordered pairs from A and B. Therefore, A cross B is set of ordered pairs A, B such that A is in set A and B is in set B. For example, if we have a set A having elements 1, 2, 3 and set B having elements x and y, the Cartesian product of these sets A cross B is having pair of elements 1, x, 2, x, 3, x, 1, y, 2, y, 3, y. It is also to be noted that in a pair of elements, the second element is called the image of the first element. There are some points to remember in the Cartesian product of sets. In a Cartesian product of sets, two ordered pairs are equal if and only if the corresponding first elements are equal and the corresponding second elements are also equal. For example, ordered pair A and B is equal to ordered pair C and D if A is equal to C and B is equal to D. Further, if number of elements in set A is P and number of elements in set B is Q, then the number of elements in the Cartesian product of sets A and B is P times Q. Further, if either set A or set B is infinite and the other set is not empty, then their Cartesian product is also infinite. Lastly, like ordered doublets A, B for product of two sets, we can have ordered triplets A, B, C for Cartesian product of three sets and so on. Now let us take an example. We are given two ordered pairs x minus 1, y plus 4 and 3, 4. We are also given that these ordered pairs are equal. We are required to find the values of x and y. Since the ordered pairs are equal, we have x minus 1 equals to 3 and y plus 4 equals to 4. This gives x equals to 4 and y equals to 0. us take a set A of natural numbers and a set B of integers and we start pairing them. But this time, instead of pairing each and every element of set A to each and every element of set B, we pair the elements based on certain relationship. The relationship we define here is that the first element of a pair is the square of the second element. Therefore, from set A, we pair the element 1 to 1 and minus 1 of set B, and we pair element 4 of set A to minus 2 and 2 of set B, and we pair element 9 of set A to minus 3 and 3 of set B. We write the pair as follows: pair 1 comma minus 1, pair 1 comma 1, pair 4 comma minus 2, pair 4 comma 2, pair 9 comma minus 3, pair 9 comma 3. This set of pairs is a subset of Cartesian product of sets, and this is called relationship from A to B. Therefore, we see that a relation R between a non-empty set A and a non-empty set B is a subset of Cartesian product of sets A and B. The subset is derived by defining a relationship between the first and the second element of the ordered pairs in A cross B. Therefore, we write relationship as relationship from A to B is equal to set of ordered pairs X and Y such that Y is equal to Rx, where R is any relationship. The second element in the ordered pair is called the image of first element. The set of first elements of the ordered pair is called domain, and the set of second elements is called the range. The entire set B is called the codomain of relation R. Therefore, in the example that we have seen earlier, the relationship from A to B is written as set of ordered pairs X and Y such that X is equal to Y square and X is in set A and Y is in set B. The set of first elements in the relation that is 1, 4, 9, this is called the domain of the relationship, and the set of second elements that is minus 3, minus 2, minus 1, 1, 2, 3, this is called the range. Now there are any number of relationships that can be defined from set A to set B. Suppose that the number of elements in set A is P and the number of elements in set B is Q. So the number of elements in the Cartesian product of sets is P times Q. Therefore, the number of relationships that can be defined from A to B is the number of elements in the power set of A cross B. Therefore, the total of number of relationships that can be defined between A and B is 2 to the power P times Q. Does this mean that this many relationships exist between A and B? Possibly not. But this is the maximum number of relationships that we can look for between A and B. Now let us revisit the previous example. In that example, we have paired elements of A and B such that the first element of the pair is square of the second element. In this example, we can see that first element does not have a unique image in set B. For example, element 1 has two images, minus 1 and 1. Element 4 also has two images, minus 2 and 2. And element 9 also has two images, minus 3 and 3. Now, if we interchange the sets and take set A as set of integers and set B as set of natural numbers, and we do pairing such that the second element is square of the first element. Therefore, we pair minus 1 to 1 1 to 1 we pair minus 2 to 4 and 2 to 4, and we pair minus 3 to 9 and 3 to 9. We write the pairs as minus 3 comma 9, minus 2 comma 4, minus 1 comma 1, 1 comma 1, 2 comma 4, 3 comma 9. Here we can see that each element of set A is having only one image in set B. This type of pairing is called function from A to B. Now we can formally define a function. A relation f between a non-empty set A and a non-empty set B is a function if every element of A has only one image in set B. Therefore, function f from A to B is a set of ordered pairs A, B such that f of A equals to B. The first element in the pair is called the pre-image of B under F, and the second element is called image of the first element under F. Therefore, in the example that we have seen, f from A to B is set of ordered pairs minus 3 comma 9, minus 2 comma 4, minus 1 comma 1, 1 comma 1, 2 comma 4, 3 comma 9, defined as set of ordered pairs x comma y such that y is equal to x square, where x is in set A and y is in set B. The domain of this function is the set of first elements of the ordered pairs, and it is equal to the set of minus 3, minus 2, minus 1, 1, 2, 3. The range of this function is the set of second elements of the ordered pairs, and it is equal to the set of elements 1, 4 and 9. Now that we have seen the definition of functions, it's time to see some of the common functions. The first common function is identity function. The identity function is a real valued function defined by y is equal to fx is equal to x. Therefore, in this function, in the ordered pairs of this function, the first element is equal to the second element. The graph of this function is like this. The second common function is a constant function. A constant function is a real valued function defined by y is equal to fx is equal to c. Therefore, the range of this function is a constant value and the domain of this function is a real number. Graphically, this function is shown by a straight line parallel to the x-axis. The next common function is modulus function. A modulus function is a real valued function defined by y is equal to fx equals to x if x is greater than or equal to 0 and equals to minus x if x is less than 0. Therefore, the domain of this function is all the real numbers and the range of this function is only positive real number. The graph of this function looks like this. It looks like v. The value of y is always positive whatever the value of x is. The next common function is Signum function. A Signum function is a real valued function defined by y is equal to fx equals to 1 if x is greater than 0, equals to 0 if x is equal to 0, and fx equal to minus 1 if x is less than 0. The graph of this function is a step function. The maximum value of y is 1 and the minimum value of y is minus 1. Therefore, the domain of this function is set of real numbers and the range of this function is only 1, 0 and minus 1. The next common function is greatest integer function. This function takes the real value of x and returns integer value which is just smaller than the value of x. Therefore, if x is between 0 and -1, it returns -1. If x is between 0 and 1, it gives the value 0. If x is between 1 and 2, it gives the value 1. If x is between 2 and 3, it gives the value 2, and so on. Therefore, the domain of this function is all real values of x, and the range of function is only integer values. Graphically, this function is shown like this. Next common function is polynomial function. A polynomial function is a real valued function defined by y is equal to fx equals to a0 plus a1x plus a2x square plus a3x cube plus a4x to the power 4 and so on. a0, a1, a2 etc. are the constants. If all the constants except a0 and a1 are 0, then it is a linear function. If all the constant except a0, a1 and a2 are 0, then this is a quadratic function. And if all the values except a0, a1, a2 and a3 are 0, then this is a cubic function. The quadratic function is shown by this curve, and the cubic function is shown by this curve. The domain and range of the polynomial function both are real values. We have defined some common functions. We also observed that we can perform operation on real functions to create new functions. Let us take two functions f and g, both operating on real values of x. Addition function f plus g of x is defined as f plus g of x is equal to f of x plus g of x for all values of x belonging to the set x. Similarly, subtraction function f minus g of x is defined as f of x minus g of x. Similarly, we can define multiplication operation on real functions. Let us again take two functions f and g, both operating on real values of x, and let us take alpha as any scalar. Scalar multiplication function alpha f is defined as alpha f of x equal to alpha times fx. And multiplication function of two functions fg is defined as fg of x is equal to f of x times g of x for all values of x in the set x. In a similar way, we can define quotient of real functions. Let us again take two functions f and g, both operating on real values of x. Quotient function of f and g is defined as f by g of x equal to f of x divided by g of x. Provided g of x is not equals to 0 and x is in set x. Take an example. Suppose that f of x is equal to x cube and g of x is equal to 2x plus 1, and suppose that the scalar value alpha is equal to 10. The addition of these functions results in f plus g of x equal to f of x plus g of x equals to x cube plus 2x plus 1. Subtraction on this function gives f minus g of x equals to x cube minus 2x minus 1. Scalar multiplication of f gives alpha f of x equals to 10x cube, and function multiplication gives f of g of x equals to f of x times g of x equals to x cube times 2x plus 1. Performing the division operation, we get f by g of x equal to f of x divided by g of x equals to x cubed divided by 2x plus 1. To summarize, in this lecture, we have learned Cartesian product of sets. We have learned the definition of relations from one set to another. We have learned the definition of functions from one set to another. We have seen some common functions like constant function, Signum function, Modulus function, polynomial function, etc. And we have seen how to perform operation on real functions.